Hey everyone, and welcome to the wonderful world of organic chemistry. So first thing I have to ask, I know you've all heard the word organic before, so think, what's the first thing that pops into your head when you hear that term, besides chemistry, of course? For most of you, you're probably thinking of, you go to the supermarket and you see organic products, organic ketchup or organic potatoes. Think of things being natural. Okay, and that's not far off from the original origin of the word organic. So a few centuries ago, organic molecules were believed to have been distinct chemical molecules that were only found and only produced inside living organisms. Okay, things like your blood, for example, something that you can't just produce or make in a lab. Okay, so this was believed for years and years, these organic molecules, until in 1828, when a German chemist by the name of Friedrich Wöhler synthesized urea using an organic compound, ammonium cyanate. Okay, and this was the first instance of a biological compound being made in a lab. He wrote his friend, and in his letter he said, "I must tell you that I can make urea without the use of kidneys, either man or dog. Ammonium cyanate is urea." And it's not that ammonium cyanate is urea, but upon heating can produce urea. This changed the world of chemistry drastically from this point on, because now it opened up a whole new branch of synthesis, of this making of organic compounds. Now, what is meant in chemistry by organic compounds? So when we talk about organic, what we're referring to is the chemistry of molecules that contain carbon. Okay, and that's the definition that we're going to be working with in the branch of organic chemistry that we study here. One of the special properties about carbon, which is why it gets its own entire branch of study in chemistry, is the fact that it can form four bonds, and also it can form bonds to itself. Okay, so this allows it to produce these very long chains and ring molecules. It can actually, there's literally millions upon millions of carbon-containing molecules that are known to exist, from the very simple methane to the very complex heme B, which is found inside of our red blood cells. Since there are so many carbon-containing molecules, we need a classification system. So we group different carbon molecules, different similar carbon-containing molecules into families or series that we call homologous series, and we base what's in here based on the functional group that's part of the molecule. We'll get into functional groups in a little bit. The first homologous series we're going to study is the alkanes. Okay, so an alkane, or a hydrocarbon, contains only carbon and hydrogen. Okay, and just singly bonded carbon-hydrogen molecules. The smallest one in the series is methane. Then if we add a CH2, we get ethane, add another CH2 to propane, another CH2 to butane. Okay, so we can see that each successive member in a homologous series has the addition of a CH2 group. Members of a particular homologous series share the same general formula and also the same functional group. What a functional group is, again, we'll get into that later on, but that's, for example, alcohol, carboxylic acid, when we add a different piece to the molecule besides just the carbon and hydrogen. Sticking with alkanes for now, though, the general formula is CnH2n plus 2. So by using this formula, it allows us to determine the formula of any alkane given just the number of carbons in the molecule. So looking at that chain of alkanes from methane to butane, you'll notice that they all contain similar atoms, okay, which means that all of these molecules, similar atoms in the same structure, they'll all have similar chemical properties. So of any homologous series of alcohols or of carboxylic acids will always have similar chemical properties to other members in its own series. Now, as it gets larger, though, its physical properties will gradually change in a very predictable manner. Why that is due to intermolecular forces. So if we look at the alkanes, the only type of intermolecular force present there is London dispersion. It does not have hydrogen bonding. It does not have dipole-dipole. It is a nonpolar molecule, so we have London dispersion forces. These London dispersion forces, as we've learned in a previous chapter, get larger or increase with the molar mass of the molecule. So as we go up the homologous series, we'll see an increase in the intermolecular forces, which means we'll see an increase in boiling and melting point, which you can see from the table that's listed here. The first four in the series, methane to butane, are gases at room temperature, but pentane and hexane are actually liquids. Another liquid is, or anything, keep going up from that as liquids until you get to C17H36. From that point onwards, we're actually looking at waxy solids. So candles are actually just part of the alkane homologous series. In summary, what we looked at today was a little bit about the history of organic chemistry. Where did it all begin? And we checked out what a homologous series is and how to classify carbon atoms. So a homologous series, again, is a series that contains the same functional group. It has the same general formula. Each member of the homologous series differs by a CH2 group. They have, across the series, has similar chemical properties, and they show a gradual change in physical properties such as melting or boiling point.